Hello and welcome back to a video series on MAC 1105 College Algebra. My name is Sean Perry. These are guided notes number 24 in the series on section 5.2b, Logarithmic Functions, Part 2, the graphs of logarithmic functions. In the last video, we began to investigate the logarithmic functions. These are the inverse functions to the exponential function. Recall that an inverse function has a graph that is very similar to its parent function, namely, it is a reflection of that graph over the diagonal y equals x. This means that if we know something about the graphs of exponential functions, we're going to be able to determine the graphs and the properties of the graphs of the logarithmic functions. As before, it's possibly helpful to break this into two cases, namely bases that are greater than 1 and bases that are between 0 and 1. And these are going to be all the admissible bases. So let's first look at the bases which are bigger than 1. As you make x larger, this makes b to the x also larger, and it shoots off exponentially as you go towards the positive direction. So likewise, the logarithmic function with base b is going to look like the reflection of this guy over the y equals x line. So let's see what that implies in terms of some of the properties of each graph. The domain of the exponential function b to the x is the entire real number line. Even though it gets very, very steep, it is still going to have a value, just a huge value, for plugging in big values of x here. And its range, well, is only the positive numbers, right? In fact, it's not even 0. It has an asymptote in this direction towards y equals 0, but it never really gets there. It just gets closer and closer as you go towards negative infinity. And so let's even focus on that little tail here. That tail reflects down here. And in the same way that there were no negative values in this lower half of the graph, there are now no values listed in the left half of the graph for log base b of x. So just like any function and its inverse, they actually interchange the roles of x and y, and that means they interchange domain and range as well. Notice that the domain of the logarithmic function is only the positive numbers. We're not allowed to plug in 0. That's actually undefined. And we're not allowed to plug in negatives. That would actually give complex values. So we're going to throw those out for the time being. We're going to not want to focus on the complex values. We're just going to want to look at the real graphs on the xy plane. So we can see that the logarithmic function seems to be getting less and less steep. I mean, it's maybe got a positive slope over here, but it seems to be leveling off. One should keep in mind that it's going to keep rising forever. In the same way that the exponential function just gets very, very big, this function will attain every value in the y direction. You might just have to go to a very, very large x in order to get there. So that means that the range of the logarithm, whether it looks like it or not, is going to be from negative to positive infinity. It is actually going to hit every single y value on the number line. Let's look at some specific points. So this graph of the exponential passes through 0, 1, and likewise, the graph of the logarithm is going to pass through 1, 0. We're going to also pass through 1, the base. That's going to be a point on the exponential. And so if we want to get to the y value of 1 on the logarithmic function, we'll have to go over to the x value of b, the base. Finally, let's look at those asymptotes one more time. We have this, at least on the left-hand side, on the negative side, we have a horizontal asymptote here for the exponential. It's getting closer and closer to y equals 0. And likewise, for these negative values of y, as we get closer and closer to 0, the graph is shooting down towards negative infinity. And so we have a vertical asymptote here pointing down in the negative direction at x equals 0, the line. It is hugging the line, x equals 0, the y-axis, for the logarithmic function. Now let's take a look at the other case, the case where we're talking about b, a value between 0 and 1. So like a half or a third or some other proper fraction. And we can see that this has had the effect of sort of flipping the graph around for b to the x, right? It's almost a horizontal reflection of b to the x. And in the same way, our log has now been vertically reflected. So let's see what that implies. The domain and range have not changed. The domain of b to the x is still the whole x number line. You can plug in any value you like, you can raise b to that power, and you're either going to get a very small number if x is large, or a very large number if x is small in the sense that it's negative. We're still going to pass through the same points, 0, 1, and 1b. But now b is sort of crunched in between 0 and 1. So that's getting a little hard to graph right there. But we have 1b, that would be here. And in the same way, b1, so here's a b and here's the value 1, this would be a point on the logarithm. But it's a little bit easier to see, I think, what happens, at 1 over b. But we'll look at that more carefully when we get into the problems here. For now, I just want to at least mention that they both are still going to pass through these axis points. So we have b to the x going through 0, 1, and log base b going through 1, 0. Now, our asymptotes have switched, right, in the sense that instead of being a horizontal asymptote going into this negative x direction, we now have this tail pointing in the positive direction. And likewise, the tail, or the vertical asymptote of this logarithmic function, is pointing positively. But we still have the same equation for those asymptotes, y equals 0, x equals 0, respectively. So our questions are going to start off with some matching. We want to match a graph with an equation. And the equations they have in mind are these simple linear transformations of some parent function, log base b of x. So let's look and find that parent function here, right? Our log base 4 of x doesn't have anything else going on with it. There's no, minuses or plus constants or anything like that. So this is going to be our parent function. Let's sketch a graph of that, and then we will apply these transformations in turn. So for the most part, we can graph this by remembering what direction the asymptote's going to go. This is a base 4, and so we're going to have an asymptote pointed down vertically towards negative infinity here. It's going to go through 1, 0, as all logs do. Well, all logs that aren't sufficiently messed with. We're going to see that in just a moment, but our parent function, log base b of x, is always going to go through 1, 0. And it's also going to go through the base 4 and 1. Remember that the logarithm tells you what power you need to raise the base to get a certain number. And so if I plug in 4 here, it only needs to be raised to the power of 1 in order to get 4 itself. And so it needs to go through these 2 points. I think that looking at these 2 points and where the asymptote goes is very helpful when we're trying to determine what's going to happen to this graph under transformation. So now let's walk through these transformations and then we'll match them to our graphs. The first one has a negative sign on the inside, multiplied against this x is a negative 1. That's going to tell us this is a horizontal reflection. And also there's a negative sign outside, which tells us that's a vertical reflection. Remember, that's a reflection over the y-axis and over the x-axis, respectively. This next one is just a horizontal reflection over the y-axis. This one has subtraction by 1 on the outside. So remember, subtraction or addition of a constant is going to shift it. We're on the outside and it's negative. We're going to shift this down by 1. This is our parent function. Now we have a minus 1 on the inside. So we're subtracting 1 on the inside. And that's going to tell us that we are moving to the right against the sign by 1 unit. Finally, this last one just has a negative sign on the outside. It's multiplying. That means it's going to be reflection. And so we're going to have a vertical reflection or reflection over the x-axis for this one. So now let's go through each one of these graphs and see where it goes. Let's look at the parent function first. So here we can see, just by matching the 2 pictures, it goes through 4, 1, it goes through 1, 0, tails pointed down, asymptotes against the y-axis. This is our original function. Now, how do I reflect that? I don't know, let's say vertically. To reflect it vertically, I just take all of my y values and negate them, and that flips this tail upward. It flips this 4 down here to a minus 1, and so this is going to be our graph. Let's look at b next. This is a multiplication by negative 1 on the inside. That's going to be reflection over the y-axis, or horizontal reflection. So that's going to take all of my x values and negate them, but keep the y values the same. So notice now we are at negative 4, 1, negative 1, 0. But my asymptote, which was at x equals 0, is still pointed down along that y-axis for its vertical asymptote. What about both of them? What if we did both of them? Well, either take this one and reflect it vertically, or take this one and reflect it horizontally, and you'll get this one here. Either way is fine. It can be done in either order. You get the same thing. How about our shifting problems? Well, C says downshift it by 1. So we take our parent function and we scooch every point. Every y value goes down by 1. Notice this didn't change my asymptote, my vertical asymptote at all. I just kind of slid it down along that asymptote. So vertical transformations are going to leave the asymptote in place. But 1, 0 is now at 1 minus 1, and 4, 1 is now at 4, 0. The y value is decreased by 1. Likewise, this one's going to give us a right shift. We're actually going to get to those values 1 later by subtracting 1 in here. That is to say, when is this parent function have a 0 for its argument? At x equals 0. Where does this parent function have a 0 for its argument when x is 1, moving it to the right? So taking all of my x values and increasing them to move it to the right, that's going to give us this purple graph here. Okay, moving on. Here we have precisely the same setup. The only difference is that we are shifting by 2 perhaps, and our parent function has a proper fraction for its base. We have a base of 1/4. So let's remember what that looks like in terms of its logarithm. Its parent function is going to have a vertical asymptote, which points upward instead of downward. It does go through 1/4, 1, and it goes through the usual 1, 0. Now, I think it's easier as far as plotting is concerned to, instead of trying to plot something at a quarter with a value of 1, to plot what happens when you would plug in a -1 for that exponent, right? If you took 1/4 and raised it to the -1, you'd get 4. And likewise, that means that the logarithm base 1/4 of 4 is going to be -1. So this gives us perhaps an easier point to plot than 1/4, 1. Now, some of the observant among you might have noticed that we just changed this number in the base by making it a reciprocal from the last problem. Instead of 4, it's a 4th. And the graph has sort of done this vertical reflection. Now, is that always going to be the case is a good question. And the answer is yes. We can actually see that. Let's play around with the symbols briefly. Let's say we had some value b, which was greater than 1. So if I have b greater than 1, 1 over b is a proper fraction. And what happens to log base 1 over b of x? Well, if that were equal to y, rewriting it in exponential form would look like this. This is related to a base of b by the -1 power. So if I combine those powers, I get an exponential form of b to the -y is equal to x. Let's drop that back into exponential form now with this new base of b. And that tells me that log base b of x is equal to -y. But just moving my negative sign to the other side, looking at that original y value, we can see what's happened to our function. Changing the base from 1 over b to b pulled out a negative sign. And if I'm just looking at the negative of this original equation, it's going to look like vertical reflection over the x-axis. So that's always going to be the case when we're graphing. If we have something that looks like 1 over b, we could just as easily think of that as the graph of log base b, but take its vertical reflection, which is why I think it's fairly easy to just plot the point for 1, and now we can see where these points are going to go. Let's run through these transformations. Here I have subtraction by 2 inside, that's a right shift of 2. Multiplication by -1 on the outside, that's vertical reflection, which we're going to see looks a lot like log base 4 of x. Here's our parent function. Here's horizontal reflection with a multiplication by -1 on the inside. Then we are subtracting by 2 on the outside, that's a downshift of 2. And here we have negative signs inside and outside. That's going to be vertical and horizontal reflection. Be very careful. You cannot just pull constants like -1 out of the logarithm's parentheses. It's going to hold on to those very tightly. We're going to see a way that we can sort of work around the parentheses of the logarithm in certain cases, and that will reinforce some of our understanding now about how these negatives are related to the graphs themselves. But this part here is not just log base 1/4 of x. The negatives do not cancel, and in general, you cannot pull out constants from the logarithm without some extra considerations. So this is going to be both vertical and horizontal reflection. Let's take a look at our graphs. So as usual, I think it's easiest to graph the parent function first, right? It's going to look like this. We should know how to sketch it, and then we can match that sketch to this graph. Notice it does go through 1, 0, and 4, -1. And if we could check, if they had a 1/4 here, we would see that that has a value of 1. It's got an upward pointing vertical asymptote. Its tail points up. And I should stress while we're just talking about this initially, even though it looks like it's leveling off here, you shouldn't think of it as having any kind of horizontal asymptote. It's going to get more and more negative. It's just going to take longer and longer to do it. It will eventually hit every negative number here. Okay, So what about this a? It's a right shift of 2. So we take this function, scooch it over to the right by 2. That gives us this one. What about this one, b? Well, that's vertical reflection. So we want to flip this upside down. That's this one here. And yes, it looks just like log base 4 of x. Then our parent function, then we have horizontal reflection. That's going to look like this one, but flipped over the y-axis. Here we are. Then we've got downshifting by 2. So that's taking each one of these points and scooching them down by 2. That's here. Notice it does keep the asymptote in place. And then finally, we have both reflections. We have reflecting over the y-axis and then also over the x-axis. So I think it's easier to do this in steps. Just take a look at, for example, this one, the vertical reflection, and then what happens if I reflect that horizontally as well. I'm going to get what's in blue here. You could compose them either way, and you can also, in fact, think about this as a 180-degree rotation. I'll leave it up to you to try to play with it and see that reflecting over the x and y axis, regardless of how you do it, is the same thing as rotating your graph by 180 degrees. Before we move on from this, I'd like to take a moment to show you how you could address this problem in Desmos and on your graphing calculators. Let's start with graphing a parent log function. If you use shift and the slash key, you can write in the subscript here. And I'm actually just going to use b. And when I type log base b of x, it's going to ask me if I want to add a slider. Let's do that. Our admissible values for b are going to be things which are either between 0 and 1 or are going to be greater than 1. We're not going to consider it being equal to 1, that's degenerate, and we're not going to consider what happens when it's negative. Notice that we don't wind up with any real values when we select those b's. Now, if I want something like a quarter, I can type in the decimal representation and it will produce that. Notice this does give us a really nice parent function. Here it is going through 4 minus 1 again. So now let's look at some transformations. So I'm going to add a bunch of sliders here that represent all of the different possibilities that we might want for our transformations. Let me zoom out just a little bit. So let's select these in such a way. I'm going to keep b the same, and I actually want to graph the parent function as well so that you can see, how that transformation is looking. And let's say, for example, we wanted to look at this first one that just has a minus 2 here. So that corresponds to the value d. The value of v in this case, well, there's no v there, so we would just zero him out. And the values of a and c, well, you can see there's no coefficients in either spot, so we can leave those set to 1. If I want this to be a 2, I can move my guy up to 2. And you can now see that we've just taken the red function and we've scooched it over to the left by minus 2. But this is minus 2, so let's bring this back and set it to negative 2. And that's going to scooch it over as such. Let's look at one more example like this. Let's set this back to 0. And let's take a look at the one that reverses the signs, that has a reflection on the inside and outside. So I'm going to have d be equal to 0. I'm going to have v stay equal to 0. No vertical shifting here. And I'm going to set the other ones, a and c, both equal to minus 1. There you can see our scaling. And when it's minus 1, we're not going to change the shape of it at all except for reflection. And that has now been vertically reflected. Remember, outside things correspond to vertical reflections. And then on the inside, I'm going to switch this to minus 1 itself. And notice that does indeed look like 180-degree rotation. That is what we get when we have a combination of vertical and horizontal reflection. If we wanted to, we could do the same kind of stuff on the Texas Instruments. I'd go to y equals. I would type a log with the particular base that I was interested in. And maybe that's a good parent function. If I wanted to compare that with some other function, I could repeat the calculation, just changing what I need to change. Mutatis mutandis. So let's say I wanted to downshift it by 2. Let's take a look at these graphs. Now, one issue with these graphs is they're not color-coded very well, and because this dives towards the vertical asymptote, it actually can get very, very tricky to see, what's going on there. How is this vertical asymptote really looking? But this does give us a good enough graph that we could probably match it. We could see that this is, got a tail pointed up, and the other part is pointing off in this direction. We could also zoom in just a wee bit. Let's see what that does for us. So here I am centered at the origin. I'm going to press enter to zoom. And we can see this one is going through 1, 0, has this asymptote pointing up. And this one also has an asymptote pointed up, but it goes through 1, minus 2, as opposed to 1, 0 here. So I'm going to reset these back to their base values so that the two graphs overlap, because I think this is a good time to address one other thing that we sort of glimpsed when we saw transformations of functions. We only saw it briefly, though, and that is, what does the C and D have to do with horizontal translation? Notice that if I alter D, I do get horizontal translation. In fact, if C is just 1, then I get horizontal translation by exactly the amount D, right? This has shifted it to the left by 6 when D is 6. But if I alter C, notice that this also affects the scaling, right? It also affects, and kind of in this non-linear way, it affects slow over here, it affects fast over here, right? There's something going on with the relationship of C and D that determines the exact amount of horizontal shifting. So, because we're also scaling, and that's going to affect it. Something interesting, something a little bit complicated that we'll have to meditate on when we look at horizontal shifting if there's both a C and a D present here, if C is something other than 1 and D is something other than 0. So put that on the back burner, and we'll come back to that at the end of this video. Okay, so the next one asks us to graph the following equations, and notice that they are all untransformed. The only thing that's going to happen is we are changing the base of each one. And we're going to see what that does to their graphs below. So here I've provided some sketches of these graphs. They are color-coded. They all have the same negatively pointing vertical asymptote, where their tails are all pointed down like this. And they all go through the point 1, 0. When x is 5, function h is going to go through 5, 1. When x is 7, function f is going to go through 7, 1. And when x is 10, function g is going to go through 10, 1. So they go through different points. They all pass through this common point. They all have this common tail. But other than that, they have distinct points from each other. And the easiest way to see which one's on top is to point out when they're going to be equal to 1, which is going to be at the value of x of their base. But let's notice that they all have some things in common, right? Any log base b of x is going to have a domain from 0 to infinity. There's nothing over here that we can see in the half plane where x is negative. And their range, well, even though they look like they're leveling off, we saw because they're inverses of some base to the x power, and that has entire domain, these must also have entire range. They're going to hit the entire y-axis eventually, right? Every y value will be used. It just might take us a really, really, really long time to get there. For example, what about this function log base 10 of x? When is it going to be equal to 2? Well, not until x is equal to 100 will that be equal to 2. So we'll have to go very, very far indeed just to get it to 2. So they are very slow growing. That's true. But they don't level off entirely. They will always pass any upper bound eventually, and so have the following range. They all have the same vertical asymptote, though. The y-axis, aka x equals 0, is a boundary for all of them that they seem to run up against and then hug that all the way down to negative infinity. So that's their vertical asymptote. Here we have 3 other functions. Notice these all have the same base 10. If we don't see a number written in the base, we should infer that it's base 10. The only thing that's changed is we have one parent function, and then we have these 2 transformations of the same kind. One is a upshift by 3, the other is a downshift by 2. So that should be a 2, actually. So you can see that kind of spaces them out in this way, but certain things did not change. Their domain did not change, still from 0 to infinity exclusively. It's undefined at 0. We leave that out with the parentheses. Still having the same range. They're all going to increase indefinitely. They all plummet down to negative infinity, so we have the following range. And the equation of the vertical asymptote is still the same for all of them. X equals 0, aka the y-axis. So vertical transformations didn't really change much at all about the domain, about the range, or about the vertical asymptote. On the other hand, for this next one, we can see that we have a parent function. All of them have base 3, and here we have some horizontal transformations. One that's going to shift us to the right by 7, and one that's going to shift us left by 2. So that is going to affect things a little bit, right? My parent function g is going to be of the same domain and range as last time, same vertical asymptote. But now let's take a look at f. F has been right shifted by 7. So if I go right by 7, that includes my vertical asymptote getting right shifted by 7. So we have a vertical asymptote at x equals 7 now. And it's only defined, that is to say, it's only going to give us real values for numbers greater than 7. That will make sure that the argument of this log is positive. The range, however, does not change. This is still going to expand up and down forever. It goes down very quickly and it goes up very, very slowly, but it still goes up forever. H, same idea. You're going to scooch that to the left. That includes its vertical asymptote, so that's now at x is minus 2. Its domain is all the values that make its argument positive, so we have to be at least larger than negative 2. And the range, again, it rises forever, albeit slowly, and it plummets down to negative infinity. So we're going to have the range negative infinity to positive infinity for that one as well. What we're going to see is we could have actually phrased all of those domain questions as inequalities, asking us, where is this argument, x, x minus 7, x plus 2, where is that greater than 0, because we need that argument of the logarithm to be a positive number in order for the logarithm to be properly defined. All right, the following few problems are going to ask us about other transformations of these graphs. So here we have a log base 6 type function, and they have composed that with x plus 9. So we have to know that that's going to give us a left shift by 9 and be able to select that transformation appropriately. I like to make a quick sketch of the parent function, right? Log base 6 of x, which would have a vertical asymptote pointing down along the y-axis, would go through the point 1, 0, and would go through the point 6, 1. Now, let's take a look at what happened to our vertical asymptote at the y-axis. That's going to go over by 9 to the left, and so we'll have a vertical asymptote here. The point 1, 0 would have been shifted 9 units this way, down to negative 8. And the point 6, 1 would have been shifted 9 units down. That brings us to negative 3, 1. So that's usually enough that we could plot a function from that. What happened to its domain? Well, it's been left shifted from 0 to infinity to negative 9 to infinity. Those are the values which would have x plus 9 greater than 0. The range is still entire, negative infinity to positive infinity. And our equation of the vertical asymptote has gone from x equals 0 to x equals minus 9. Here's one that seems to have 2 transformations, and we have a base of 5. So let's take a look. Here we are right shifting by 1. That's this composition with subtraction by 1. And then on the outside, we have multiplication by a negative 1. Okay, that's going to be vertical reflection. So we want to do both of those things. Remember, vertical reflection goes over the x-axis. You'll see that written this way here. And we're also going to want to shift it 1 unit to the right. Remember, that moves against the sign. So when I'm doing something like this, I do want to plot the parent function first. I think that makes it easier to look at. This, we can see, has a vertical asymptote along the y-axis. It's going to get shifted over to the right by 1. So let's just plot that real quick. If memory serves me, you need to plot a vertical asymptote and then 2 points in order to plot the logarithm on MyOpenMath. So let's see what happens to these 2 points. 1 point would have gone from 1, 0 over by 1, so it's going to be at 2, 0 over to the right by 1. Now, what about 5, 1? Well, that's going to be at 6, 1. Here's another point. And then we're going to want to connect these dots and orient the asymptote appropriately. Oh, wait, all I've done is start to right shift this. I've forgotten we have 2 transformations, don't we? We have to reflect over the x-axis. So this point is going to change its sign and will now be down here at 6 minus 1. This one is also changing its sign, but the sign of 0, if you change its sign, it's just 0. So points on the x-axis don't move when you vertically reflect. But our tail, which was pointed down, is now going to have to point up. So we're going to have some asymptote which looks something like this. It's going to bank up, hit this point, continue on, hit this point, and continue. So what are our domain and range here? Well, our domain is going to go from positive 1 up to infinity. Our range is still entire. It's going to be the entire y-axis. Every y value gets hit eventually. And the equation of this vertical asymptote is going to be the vertical line x equals positive 1. The horizontal translation will affect this position, but the vertical reflection will not affect it, neither its range nor its domain. All right, here we have another one that just has some shifting transformations put on it. We're going to the right by 3, and we are going up by 4 units. and nothing else is being done. This is just addition and subtraction outside and inside respectively. We have a base of 4, so it might be helpful to look at the parent function. But really we just want to take these 3 units to the right and 4 units up for these 2 points. And that should be enough along with our asymptote to plot the graph. So here's our asymptote. It's moved when we horizontally translated by 3. I want my point, which is at 1, 0, to go over 3 and up 4. So there it is. And then I want my other point, which is at 4, 1. I want that to go over 3, up 4. There we have it. So now that tells us about how to connect this whole graph together. We haven't vertically reflected, so we're still going to have a downward pointing asymptote along this vertical asymptote line here. And then this is going to go up through this point and over. Again, nothing about our vertical transformation really changed. The domain, range, or vertical asymptote questions, it was the horizontal translation by 3 which did that. Now, one thing I just want to mention, which we'll see in more detail later, is how I could have answered that domain question with some inequalities, right? The domain of any log base b of any function, regardless if it's just some simple linear function or if it's something fancier, is still going to be the values of x such that that argument is positive. In other words, the values of x such that x minus 3 in our case right now is going to be strictly greater than 0. So solving that by moving the 3 over, we must have x be greater than 3, which in interval notation looks this way. The next one's a bit different. It wants us to graph 7 to the x and log base 7 of x on the same set of axes. And it also wants to graph the identity function. And then we can look for symmetry. We know that we're going to find symmetry. We've already kind of talked about how inverse functions are symmetric by reflection over the y equals x line. But let's see that by plotting them. So here I've plotted those 2 functions. We have 7 to the x. Remember that goes through 0, 1 and also 1, 7. And then it has this sort of exponential decay as we go to the left. This is technically exponential growth, but I'm talking about going to the left. We have this tail. And then here we have g of x equal to log base 7 of x. It goes through 1, 0, it goes through 7, 1, and its tail points down. And plotting y equals x, or h of x equals x if you want to look at the notation from the problem, then we have this diagonal line. So we can definitely see that these are reflections about that line. We can also see what I kind of alluded to in the intro, which is that their domain and ranges have switched places, right? Domain of f is the range of g, and the range of f is the domain of g. And this is, of course, because inverse functions interchange the roles of x and y, and so they interchange the domain and range. Okay, one more quick look back at the function transformations. This is similar to the first problems. We want to identify a parent function and give that a sketch. We want to identify each one of the transformations at play: horizontal reflection, upward shifting by 3, leftward shifting by 3, vertical reflection, and vertical and horizontal reflection. And then we want to pick which graphs do that. So let's take a look at the parent graph, find it. Notice we can't see it go through 10, 1. The graphs are too small, but we can see what direction the tail points in, and we have this sort of sense that it's going to get there eventually as we go to the right. We have that sort of up, we have that sort of swoop that goes along with the shape right here, and it's pointing in the right direction. So let's take this as our parent function, and let's just take that point along with the tail's direction and use that to get the rest of these. If I upshift this by 3, this point is going to go up by 3. There we are. If I shift this left by 3, this point is going to go left by 3. There we are. And if I do something that has some reflection to it, this one is horizontal reflection over the y-axis. There we are. Vertical reflection. Oh, that's a mistake. That shouldn't be. That's not vertical reflection. So that must be wrong as well. So let's correct that. Your vertical reflection should be here. You can clearly see that the tail should just be pointing up, and this point on the x-axis should remain right where it is. And by exclusion, or just thinking about 180-degree rotation, we can also see that this must be the combination of reflections. Okay, so the next question is a domain question that has a little bit more spice to it. They're asking us about a logarithm composed with x squared minus 25, the polynomial. So this is a reason why you cannot forget your tricks for dealing with polynomial inequalities, because solving this domain question is intrinsically a polynomial inequality. We want to know what x values will keep x squared minus 25 greater than 0. So how do we solve something like that? Well, we have it already sort of set equal to 0, or with 0 isolated over here, so we should factor. Once we factor, we can see that the possible changes in sign are going to happen at -5 and 5. And plugging in a test value or, looking at the multiplicities, we know that it's going to be positive in these two regions. So these are admissible into my domain, while this region inside is not, where we have to make sure that the argument stays positive. So that tells us that this is going to be our domain. Notice we do exclude those endpoints. This is always exclusive inequality or strict inequality because log is going to be undefined if its argument is 0, and it'll be some multi-valued complex function if it's less than 0. So we throw out the negative for that region, and we throw out the endpoints to make sure everything stays defined. So if we wanted a number line graph, it would look like that. Let's take a quick look at Desmos and see what this thing looks like. So we have something that looks vaguely logarithmic over here. That's nice. But it also has another branch over on this side. And it seems to have this extra wide gap. Let's zoom out a little bit, where nothing seems to be happening. In fact, it's going to kind of die off here because it's getting too close to 0. It's shooting way off down towards negative infinity on these edges. And these edges, you can see that their vertical asymptote are these lines x is equal to 5. That's one vertical asymptote. And over here as well at -5. And then in between here, even if we zoomed out quite a bit, there's not going to be any graph in that region, but there are these logarithmic looking graphs on the left and right, corresponding with these particular domain intervals. All right, moving on. The next questions ask us domain questions about a variety of logarithms. It doesn't matter what the base is. The only thing that matters is that we keep the argument positive. And that means solving these inequalities. Remember, all your rules about inequalities still follow. If you divide by a negative or multiply by a negative, you have to flip the direction of that inequality. And that does flip this domain so that we're going from negative infinity up to 2 in this case. Your vertical asymptote will be at the number that forms one of those endpoints. Likewise here, moving my -6 over, dividing by 2, I get x is greater than 3. That's this interval, and we will have a vertical asymptote at x equals 3. Here we have another polynomial inequality, right? We just factor that and use those two zeros, those two roots, as our points. If there's a negative sign up front, that might change things, but as it is, this is an upward-facing parabola, and so we know it's going to be positive in these two regions here, which constitute our domain, and these numbers give us our values for our vertical asymptotes. Problem 20 is no different. You're either solving this, and here, notice I'm dividing by -2, against +4, that gives me -2, but I have to flip the inequality, and that gives us this interval here with a vertical asymptote at x equals -2. Now this one over here, we are dividing by 3. Against -12, yes, but the object of division, or multiplication by a third, if you like, is positive. And so this will not change the direction of the inequality. We will have an asymptote along the line x is equal to -4. Okay, let's look at this last polynomial inequality one. We want to know where is this polynomial positive. So we write that out as an inequality, we factor, and we take those two roots, 1 and 6, and we put them on a number line. This is upward facing, these are multiplicity 1, however you like to see it. You can even plug in test values from each space. If you want to plug in a test point, we're going to have to pick something between 1 and 6, so maybe something like 3. That's going to be a negative times a positive, so we get a negative here. Plugging in 0, for example, I'll get a positive. Right? And so we're going to be looking at x's in these two regions here, either from -infinity up to 1 exclusively, or from 6 exclusively up to infinity. And we'll have our vertical asymptotes at these two places as well. All right, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies, and I'll see you in the next one.